Hi everyone, thank you very much for joining on today's session. Just wanted to give you a few tips, short tips, how you can interact afterwards. So you will be able to ask questions after the presentation through the WebEx client. So at the bottom, at the right side of your screen, you will be able to post your question to your panelist and receive an answer. So I would like to welcome today Jeffrey Richter, who is a software engineer from Microsoft Azure team and will be presenting today.
Well, welcome everybody. Thank you for having me. I'm going to talk about building responsive and scalable .NET applications and components. And specifically, we're going to look at performing IO-bound asynchronous operations. I'll just briefly mention that I have another slide deck where I talk about how to do compute-bound asynchronous operations, but most people don't have compute-bound problems to solve. Most people are worried about IO-bound problems, and so we're focusing on the thing that I would say 99% of the people actually care about. So without any further ado, I'll just have a quick slide here, a little busy slide, to introduce myself. I'm now a Microsoft, actually software architect is my new title. I'm also a co-founder of a company called Wintellect. We do training and consulting services. We've been around for about 17 years now. Most people are familiar with me because of the various books that I've authored. At the bottom of the slide, I show my 3 most recent books over here. And then I put my contact information in the top left. And then just last week, or maybe it was 2 weeks ago now, I came out with a new video series on YouTube, so it's completely free to everybody, called Architecting Distributed Cloud Applications. And I put the link here, and this is just one of the screenshots. There's 53 videos, and it's 6.5 hours worth of content. And I just posted that recently. So feel free to check that out. And I would love it if you enjoyed it, that you would post it and let other people know that it exists. Again, it's free. I'm just hoping that people will find it valuable. Okay, so that's it about me. So now we'll start talking about the asynchronous programming. So if you go back in time and you look at early operating systems, there was no concept of this thing called a thread. In effect, there was one thread that ran throughout the system, but we didn't call it a thread, and we didn't use the term threads for anything. And the problem that existed in these early operating systems was that a long-running task affected all applications and the operating system itself. For example, it was common when I used to use Notepad in Windows 3.0, for example, the 16-bit version of Windows. When I would use the Notepad app, if I would tell it to print the document, the printing took such a long time that the whole operating system was completely frozen. I couldn't type in Notepad, I couldn't switch to another application, nothing would work at all until the printing job had completed. And certainly if I was building my own application and I had a bug in it where the application went into an infinite loop, the entire machine would completely hang, and I would have to literally power down the computer, power it back up, restart, re-log in. All the applications I had been running, they had been killed. Any data that I had typed into those applications that were running, that data had been destroyed if I didn't save it to disk first, and I would have to re-enter all of that. Needless to say, this was a horrible experience for end users. And so when Microsoft was designing Windows NT, which was their first 32-bit operating system, they decided to add a feature to the operating system which is known as threads. And at the time, most computers were single CPU computers. Today, of course, it's very hard to buy a computer with only one CPU in it. It's very common to get 4 or maybe 8 or even more CPUs in a computer. That's even true of your cell phones today too. Mobile phones, they typically have multiple cores in them as well. But in the early days of the 32-bit operating system, most computers were still just one CPU inside them. And so threads were really added to the operating system for robustness reasons, so that each application would now get its own thread, and the operating system would time switch, context switch between those different threads. And if one application went into an infinite loop, it really meant that its thread was in an infinite loop, but other applications were able to make forward progress. And that made the whole system system as a whole feel more robust. So now Notepad could be printing a document, but if I wanted to Alt-Tab away to switch to Word or PowerPoint or some other application, then I would be able to do that, and I would be able to work with the other applications while Notepad was running. And no longer would I have to regain control of the computer by powering it down, powering it back on, logging back in, restarting all the apps, and I wouldn't lose any data that I had just entered into any of those apps. So that's really why threads were introduced into the operating system. Now, of course, over time, we have gotten computers that do have multiprocessors in them, and now Windows has the ability to schedule different threads to different CPUs at the same time. And because of this, multiple threads can run concurrently with each other, and that can improve the performance of our applications overall. But again, that scenario of running the system faster only happens if you're on a computer with multiple CPUs, and it only happens if your applications are compute bound. That means they're using the CPU to do a lot of computation. But as I said a little while ago, most applications are not compute bound. Most applications are I/O bound. In fact, I can prove that to you. If I bring up Task Manager on my computer right now, and we switch over to the Performance tab, we can see on the Performance tab, as soon as it appears, here we are, if we go to CPU, that on my computer I have 182 processes currently running. Those processes have created a total of 2,628 threads or so. And of all of those threads, they're using my 4 CPUs that I have on this computer 45% of the time, or maybe let's just call it around 50%. That means the other 50% of the time, none of these threads are running at all. They're not doing anything at all. And in fact, I can tell you that most of the CPU utilization is actually going to the WebEx app that I'm using to talk to you, because it's sharing my desktop and it's doing all the video processing. If I turned off WebEx and I was just working here at my computer, that CPU usage number drops way down, typically to only 3 or 4%. That means the other 96% of the time, none of these threads are doing anything at all, which means they're not using the CPU. So then what are those threads doing? They're I/O bound. They're waiting for input and output operations to occur. They're not CPU bound. They're not doing any computation at all. All right, now the next thing to realize is that threads have both space and time overhead. When you create a thread in the operating system, there is a lot of memory that's allocated. That's what I mean by space. And there's also a lot of CPU time that's required in order to allocate all that memory and to initialize it. Specifically, when you create a thread, the operating system has to create a kernel object data structure. This data structure varies in size depending on the CPU architecture that you're running on. If you're on an x86 computer, it's about 700 bytes. An x64 computer, it's about 1240 bytes. If you're on an ARM processor, that's about 350 bytes. And this kernel object contains some various thread properties, like the date and time when the thread was created, what's the current state of the thread, is it running, is it waiting to run, is it waiting for an I/O operation, and it contains the register set context. That's the set of CPU registers that are required by the CPU that's on the motherboard. In addition to the thread kernel object, every thread has a user mode data structure. Sometimes we refer to this as the thread environment block, or TEB, T-E-B for short. And this is about a 4 kilobyte block of memory, and it contains things like the exception handling chain. Whenever your code enters into a try block, a node is added to a linked list in this exception handling chain. And whenever a thread leaves a try block, then the node is removed from the exception handling chain. And should that thread experience an exception, then the operating system goes to that thread's TEB and then walks the exception handling chain to say, well, what's the nearest catch block? Do you want to catch this? No? Then let me go to the next highest catch block. Do you want to catch this? No? And it keeps going all the way up until it reaches the top of the thread stack. And if no catch blocks wants it, then we have what is, of course, known as an unhandled exception. And I'm sure you've all seen those at some time in your developer life. The user mode data structure also has things like thread local storage in it, that's TLS, and has some graphics device interface or open graphics library data stored in there too. The most significant piece of overhead for a thread, though, is its stacks. Every thread has both a user mode stack and a kernel mode stack. The user mode stack is 1 megabyte committed. That's actually on a 32-bit machine. On a 64-bit machine, I forget right now, but I think it's 4 megabytes committed, so it's much larger. And it also has a kernel mode stack, and the kernel mode stack is 12K on a 32-bit machine, and it's 24K on a 64-bit machine. So you have to say to yourself, whenever you are creating a thread, you're actually allocating 1 megabyte, or on a 64-bit machine, I think it's 4 megabytes of memory. And really, it's worse than that because that's just the user mode stack. You're also allocating a couple additional kilobytes for the kernel mode stack and the 4K for the user mode data structure, the tab, and you're also allocating the kernel object. So creating a thread really causes a lot of memory to be allocated, and then that memory has to be initialized, and that all takes CPU time. So there's a perf hit in creating threads, and destroying threads, the operating system has to clean up all that memory. So there's a perf hit in cleaning up a thread as well. Windows also has this feature where whenever a thread is created, all the DLLs in a process receive what's called a thread attach notification. And today it's common for a process to have maybe 300 dynamic link libraries that are loaded into its address space. So that means that when a new thread is created in that process, 300 functions have to be called, one in each of those DLLs, as the DLLs are notified that the new thread is being created. That is an enormous performance hit, potentially. And when the thread dies in a process, the operating system notifies all those DLLs with what's called a thread detach notification. That is, it calls those 300 functions again, and it tells them all that the thread is dying. This feature allows the DLLs to do some per-thread initialization and per-thread cleanup. That's what the attach-detach notifications are all about. And it's a nice feature to have, but it's actually a very expensive feature in terms of performance. And then, as I mentioned earlier, the next thing you must keep in mind is that one CPU can only run one thread at a time. So if you have a single CPU machine, of all those 2,000 threads I had in my system, only one of them is scheduled to a CPU. It gets to run for some period of time, and then the operating system switches away from that thread and switches to another thread. Those switches are called context switches, and they're also not free. There's a performance hit that's involved in saving the thread state, switching away from it, and then switching to another thread, restoring its state, and then letting the new thread run. And that's what I talk about on this slide here, is that every context switch requires that Windows perform these operations. It has to save the CPU registers from the actual CPU itself into the running thread's kernel objects. Then it has to, and that takes time to do that, then it has to determine which thread to schedule next. If it schedules a thread that's owned by another process, then the operating system has to switch the virtual address space for the other process. And that adds even more time overhead into the system. Then it loads the registered from the selected thread's kernel object into the CPU, and then after the switch, the CPU now suffers cache misses while repopulating its cache because it's now doing something completely different than what it was doing before. And so the overhead of context switches is very expensive. A lot of times people ask me, what is the time required to do a context switch? I don't have an exact number for you there, and it varies from one CPU architecture to another. It also varies depending on whether it's a 2 gigahertz processor or a 3 gigahertz processor. But as it turns out, the performance hit of the context switch itself is not really the worst part of the performance hit. The worst part of the performance hit is when the CPU when the CPU suffers the cache misses while repopulating its cache. And that's what makes the perf hit particularly bad. So all that I've talked about here with creating threads, which, by the way, a thread is a way of virtualizing the CPU, And every virtualization technique comes with some degree of overhead, which is what we've just talked about now. So all of this is pure overhead, and it all hurts the performance of the system. So then you might ask yourself, so why do the operating system architects and designers, why did they put this feature into the operating system if it just makes things slower and allocates more memory? And the answer is, of course, they put it in because it's required to provide end users with a robust operating system. Now, one thread could go into an infinite loop, but the other threads will periodically be switched to, and they will be allowed to make forward progress. And it's a much better end user experience, and they're willing to take this compromise of increasing memory consumption, slowing the speed of the system overall, in order to give end users a more robust, reliable system. Now, as a software developer, what is the conclusion that you should draw from this? Well, the conclusion that you should draw is that you want to avoid threads as much as possible, because the more threads you have, the more time they waste, and the more memory that they waste. But there is a corollary to that. And the corollary is you do want to use threads in order to keep your application responsive. So this would be for a graphical user interface application. You want to use threads. You want to have like one thread for the user interface and maybe some other threads that are doing background tasks. And this way, the user interface thread can stay responsive to the end user. So the user always has a good experience when clicking on buttons and list boxes and moving the mouse and menu items and so on. And another reason to use threads, of course, is to gain scalability if you happen to be on a multiprocessor machine, which, as I said, today, multiprocessor machines are commonplace. Almost every computer today has multiple CPUs in it. And so what we're really talking about in this session here today is how to wrestle with the tension. We want to avoid threads as much as possible because we don't want to waste time and memory, but we also want to use threads in order to keep our applications responsive and also keep them scalable so that we're leveraging the CPU hardware that we do have available to us so that we can make things perform quickly. All right, so as I said, we're going to focus really on I/O operations here. And let me just say one more thing before I move on, though, about the overhead. I don't have time to do it today, but when I do, I have a full version of this class. It's really a 2-day version of it. And in that version of the class, I do a demo. And in that demo, I just created a program that just sits in an infinite loop, and it just creates threads and creates threads and creates threads over and over and over again. And the threads don't actually do anything. As soon as they're created, I immediately have them called console readline, so they all just block. And they are not running. So they're not using any CPU time at all. And that program crashes after I create about 1,500 threads. And the reason is because I run out of memory in the 32-bit process's address space. I run this demo in a 32-bit process because I have only about 1.5 gigs of virtual memory. If I did the demo in a 64-bit process, I would have a lot more memory and the demo would take too long for me to run it in the classroom. But the point of that demo is to show, so you can actually see that these threads have all this memory overhead, so much so, in fact, that creating many threads causes the application to die. It just gets an out-of-memory exception, and it just crashes. I'm going to come back to that later, which is why I wanted to talk about it now. Okay, so now let's talk about how application programmers today do synchronous I/O operations. What I show on this slide here is a depiction of a typical computer system. Your typical computer has a bunch of peripherals on it, like you might have a network card, or maybe you have a Wi-Fi adapter. And then you might have a DVD-ROM drive over here. And you probably have a hard disk somewhere installed. Now, if you look at all these hardware devices closely, you can see that they have circuitry on them. You can see that clearly in this picture. And on the DVD-ROM drive, if you took the case off, you would see that there's circuitry there. And on the hard disk, if you flipped it upside down, you would see that there's circuitry on the other side of the disk. What is this circuitry? This circuitry is actually a computer. It's a miniature computer that has a very dedicated purpose in life. Its purpose is to, in the case of the hard disk, spin up the hard drive and then seek the head to the right location across the drive, read the magnetism, magnets of the bits that are on there, and then send those bits through a wire that you would connect in the back here to the motherboard, and then those bits would be placed into memory somewhere, and then you could go and read them, right? Or the computer does the reverse, and you can say, here's some bytes in memory, I want to send them across the wire, and then I want to spin up the disk, seek the head, and now I want to change the magnetism on the head so that I'm storing those bits permanently on the disk. Right. Similarly is true for the network controller, where we can take bytes in memory and we can send them over the wire to another computer. Or on the DVD-ROM drive, the computer knows how to spin the disk, light up the laser light, interpret the reflection of the laser shining off the metal disk, the silver disk, and then take the bytes that it's reading, put them through a wire that would come out the back here, and then put them into bytes of memory on the motherboard. Right. My point is, all these hardware devices come with a small, inexpensive, dedicated computer, and it's the job of that computer to manipulate that hardware device. Okay, so now let's come to your program code. Let's say that you want to go and read some bytes from a file. So in .NET or C#, the way you would do that is you would new up a file stream class. That's going to go and open the file on the disk over here, and then you get back a reference to a file stream object. The next thing you'll do is you'll take the file stream object and you'll call the method read on it. And you pass some parameters to read, like the address of a byte array where you want the bytes to be placed. You want tell it how many bytes you want to read from the file and put them into that byte array, and so on. Now, when you call the file stream read method, what actually happens is your thread that's executing this code jumps from managed code into user mode or native code. And it calls a Windows function called read file, which is fully documented. You could go and look it up if you're not familiar with it. The read file function is the function that you call in order to read data really from any kind of I/O hardware device. Even though it's called read file, the function name is not completely accurate. You could also call this function to read data from a socket as well, or from other devices like a pipe or a mail slot. What the read file function does internally is it allocates a small data structure called an IO request packet, or IRP for short. And this data structure is maybe about 100 bytes in size, and it's populated with a bunch of pieces of information, like the handle to the IO device that you want to read, that this is a read operation as opposed to a write operation, the offset within the file where you want the read to begin, the address of the byte array where you want the bytes to go, the number of bytes you want to read. All of that information is placed into this IRP data structure. Once the IRP data structure is allocated and initialized, then your thread jumps from user mode down into the Windows kernel and passes the IRP data structure down to the kernel. Now your thread is using its kernel mode stack. Before it was using its user mode stack, by the way. Now the kernel, it validates the IRP data structure to make sure that everything you passed in there is valid information. And then, because this is a request to the hard disk, the kernel goes and dispatches the IRP data structure into the hard disk's IRP queue. Every hardware device, like the DVD-ROM and the network, they all have their own IO request packet queue. On the slide, I only show the IRP queue for the hard disk, but these hardware devices have IRP queues as well. Now this IRP has been queued up for this IO device, this hardware device. And the device driver will take the IRP off the queue and will go and send commands over the wire into the hardware device. This now causes the hard disk to spin up, seek the head to the right location, and do its magnetism thing to start reading the bytes off of the disk into memory. Now, while the hard disk is doing this work, what about your thread? What is your thread doing? And the answer is nothing. Your thread has nothing to do. And so the operating system simply blocks your thread here. So hardware devices do I/O operations. Threads do not do I/O operations, right? It's a very important thing to understand, right? Hardware does I/O operations. Your thread does not. Your thread queues up a request to do an I/O operation, but then the hardware actually does the request itself. There's actually no threads involved in initiating I/O operations. Now, once the hard disk has done its work, the piece of hardware is done doing the operation, then it goes and fires an interrupt. And the interrupt tells the operating system to wake up your thread that queued up the I/O request packet. So now your thread will wake up and it will be scheduled back to a CPU. That allows your thread to now return all the way up the stack from the kernel mode stack to the user mode stack. And now this read method returns the number of bytes that were read, and now your thread continues running on the CPU and doing actual work at this time. Okay, so this is what happens when we do synchronous I/O. Now, synchronous I/O tends to be very convenient as a programming model. That is, software developers like it. We've had it for many, many decades. We all know how to work with it and to use it, and so we enjoy it. However, there's a significant downside to synchronous I/O. And the problem is that the thread blocks while the I/O operation is occurring. So what that means is you've allocated all this memory for the thread, you've incurred all that performance hit of having the thread create itself, and then the thread is not running while you're doing the I/O operation. So really, it's a waste of resources. But then it will start running again. Now, in the case of hard disk, you usually make the request, the I/O operation completes, and the thread starts running. But in the case of something like network, you make the I/O request out to a server to go get some data for you, and that server could be offline. That server could be busy handling other client requests. I mean, there's no telling what that server is doing. And so it could literally take seconds, minutes, hours, or maybe the server will never return. And so now you have a thread stuck in the kernel, blocked, waiting for the server to respond, which can be enormous amounts of time. And you're just wasting resources for enormous amounts of time. So fortunately, there's a way to rewrite the code to improve on this. And that's what asynchronous I/O is all about. And in .NET 4.5, that's when the C# team added this new async await feature into the C# language. And the purpose of that feature is to give you the similar programming model that you had before, the one I just showed you on the previous slide. But while it gives you that programming model, it now allows you to not block threads so that you don't have threads that are stuck in the kernel. This allows your program to create far fewer number of threads, and you're using resources in a much more efficient way. And ultimately, this allows your graphical user interface applications to be more responsive, because if your GUI thread makes I/O operations, the GUI thread won't be blocked. It can go back to the message pump and process user input like keystrokes and mouse events, so the user has a responsive experience when working with your application. And if you're using asynchronous I/O with server-side applications, it allows you to handle tens of thousands or maybe even more client requests all concurrently using very little amount of system resources. Excuse me a moment. A lot of talking. Okay, so now let's rewrite the program I just showed you a moment ago, but now we're going to do it with this asynchronous feature so that we are using system resources efficiently. Well, I removed the other two hardware devices off the slide because I wanted to introduce the Common Language Runtime's thread pool. I'm sure many of you are familiar with the CLR thread pool, and this is basically a pool of threads that the Common Language Runtime creates for you on your behalf. And the thread pool manages thread creation and destruction for you automatically, so you yourself don't have to create threads. And it manages the thread creation and destruction in a very efficient way. It tries to really limit the number of threads that you have in your process. Because if you think about it, what is the ideal number of threads to have in your process? And the answer to that is the ideal number of threads to have is equal to the number of CPUs you have on the machine. So if you have a 4-processor machine, then the ideal number of threads to have is also 4. That way, one thread gets scheduled to each of the cores, and if you had 5 threads, then you get context switching, because now you have 5 threads that want to run on a 4 CPU machine. But if you only have 4 threads or fewer that want to run, then each CPU can be assigned a thread, and then there's no context switching because there's no other threads that want to try to run. So, and context switching, of course, as I said before, it introduces performance overhead. And then if you have more threads, only 4 of them can run at a time anyway, so the rest of them are really just all wasting resources. So the thread pool knows this, and the thread pool tries to create 1 thread per core, and then it reuses those threads as much as possible to keep your program using system resources efficiently. All right, so now let's walk through the code. First thing I do here is I new up a file stream, and I pass in a special flag this time, file options asynchronous. This flag does 2 things. It tells the device driver that owns this file that we're opening that whenever I make a request to perform an I/O operation on the file, don't block the thread that's requesting the I/O operation. And you'll see that in just a moment. The second thing this flag does is it tells the device driver to put the completed I/O request packet in the CLR's thread pool over here. And I'll also demonstrate that to you in a moment as well. All right, so now we've opened the file on the disk. And now instead of calling file stream read, I'm going to call file stream read async. Now what read async method does is very similar to what file stream read does. It internally goes and calls the same function I talked about on the previous slide, read file. Read file then does the same thing it did before. It creates an I/O request packet and initializes it. It then causes your thread to jump from user mode to kernel mode and passes the ERP data structure down into the kernel. Now the kernel takes the ERP structure and dispatches it off to the proper ERP queue. But now something awesome happens. Because we specified this flag, file options asynchronous, that told the device driver not to block the thread that's requesting the I/O. So instead of the kernel suspending your thread here so it can't run, after your thread queues the ERP into the queue, your thread now returns immediately back up the stack. At this point, read async returns a task object. And you can do lots of things with that task object. You can call wait on it. You can call continue with on it. You can whatever else. But a new thing that you can do as of .NET 4.5 is you can await the task that's returned from here. What the await operator does in C# is it allows your thread to return to the caller. So this thread that called read async is now allowed to return from this method back to whoever called it. Now, if this is a GUI application, then this is the GUI thread returning back to the message pump so it can continue to process keystrokes or mouse events. And this is what allows the user interface to be responsive so that your end user has a good experience with your application. If this is a server-side application instead, then this was probably a thread pool thread that came through here. And this allows the thread pool thread to return back to the pool where it can then be used to do other things. And we'll talk about that in just a moment. Okay, so now the device driver will take this ERP off the queue and send it to the hard disk. The hard disk will spin up, the head will seek to the right location, it will do its I/O operation, and now the I/O request packet is done. Well, if we go back here to this file options asynchronous flag, the second thing it did is it told the device driver to put the completed ERP into the thread pool. So now this ERP, when it's done, will be queued up into the CLR thread pool. It's as if the device driver is calling thread pool queue user work item, if you're familiar with that API. Or it's as if the device driver is calling task.run, if you're familiar with that API. They both do the same thing. They queue up something to the thread pool. Well, now what happens is that some thread in the pool will see that there's work to be done. It will go and extract that herb out of the pool, and then it will call back into this method, but it will resume the method after the await. So now the thread will do this assignment and return the number of bytes read. And now your code will continue executing, and now you can process the bytes that were read into the byte array. So hopefully you can see the code you write is almost identical to what I showed on the previous slide. The difference is this asynchronous flag, we're calling read async instead of read, and we're calling await over here. Everything else is identical. But the difference is that no thread is blocked now. And because no thread is blocked, we get to reuse our threads, and that allows our resource consumption to be very low in the system, and that allows our program to run faster with fewer resources and to scale better. And that's really the whole purpose of this. So to summarize it, this async await feature that was introduced in .NET 4.5 is really all about giving you, the software developer, a sequential programming model for doing asynchronous I/O operations, thereby reducing your resource consumption, right? That's kind of the elevator pitch or the summary of what this feature is all about. Okay, I normally do a demo here to walk through some code, but I'm a little bit running behind on schedule, and I'd like to get some other stuff I think is more interesting, so I'm going to skip this demo. But presumably by now you've all written some code that does async and await, and maybe you've even debugged it. I would step through to the debugger and show you where we would hit. But presumably you've all done that because the feature has been available for several years now, and hope maybe now you have a better understanding of the purpose of the feature and why you're doing it. What I do show here is kind of a walkthrough of what actually happens underneath the C# compiler. When you write code that looks like what I show at the top of the slide over here, this is down below, this is what the C# compiler is turning it into. I'll walk through it as quickly as possible. When you create a method that has the async keyword on it, you're telling the compiler to turn this method into a class. And that class represents a state machine that has different states that you can be in of the machine. And the compiler will go and add a method to the class, and it's going to return a task of int32 in this case, since that's what this method said. The method's going to return a task of int32. A task object, I'm sure you know this, identifies an operation that's going to complete in the future. And in this case, when this task completes in the future, its result is an int32. There's a parameter that got passed into here to this method. This parameter will actually be turned into a field of the class because we're going to enter and leave this method multiple times, which is the state machine method, but we need the parameter to maintain its value as we enter and leave the method. So the parameter gets turned into a field of the class, and then within the method, any code that accessed the parameter, like over here, the compiler will rewrite that code to go and access the field instead. Okay. Now the compiler goes and introduces the state machine. That's basically a switch statement that does a switch on an integer variable. This will be another field or member of the class, and it's just an integer that defaults to the value 0. And then there's a case 0 statement that the compiler generates. Now, this method has to return a task of int32. So the compiler creates code to new up a task of int32, and it puts that into a member of the class. Then we said over here we want to new up an HTTP client and call getStringAsync, passing in the parameter. Well, the compiler turns that into code that news up the HTTP client and calls getStringAsync, but here it passes in the member instead of the parameter, since the parameter has been turned into a member. This getStringAsync, it returns a task for the getStringAsync method, and that gets saved in another member of the class. The compiler then generated code to change the state from 0, which is what it gets initialized to the number 1. I'll show you case 1 in just a moment. That's in this blank area. Then it takes the task for the getStringAsync method, and the compiler calls continue with on it, so that when this operation completes, it will go and call this method again. It calls continue with on itself. But next time this method gets called by some other thread pool thread, the state will be 1 and will switch to the next state of the state machine. I'll get to that in just a moment. Then the compiler issues a break here, which breaks out of the switch, and we return the task for the int32, that's the task for HB length async, or HLA. It returns that back to the caller, because the caller needs to know the originating task for this state machine. Okay, now, the device driver, in this case would be the network device driver, is performing this I/O operation. When this I/O operation completes, the device driver will queue up the completed ERP into the thread pool. Then a thread pool thread will go and call this method again because of the continue with. When this method gets called, we'll do a switch on the state, which was set to 1 previously. So that means we're now going to jump to case 1. And we're now executing the next state of the state machine. Here the compiler wrote code to take the task object from getStringAsync and call result on it. This is going to return back the string, which is the HTML string. Now, what we wanted to do is we wanted to take that HTML string and we wanted to return that, the length of it actually, as the int32 for this task. So the compiler takes the reference to that task object that it created earlier on, and it calls setResult on it, passing in html.length, which is the same thing we had said over here. So that now sets this task as complete with this integer value. And any other thread or state machine that was waiting for this task of int32 to complete, that is now true. And another thread pool thread could wake up and now go and execute the next state of the state machine that was waiting on this particular task. And then we have a break statement here where we just return this thread, pool thread, would now just return back to the pool where it can go and do something else. Now I have one more thing to point out here. I mentioned that result here, this could throw an exception if this I/O operation completed. Let's say this URI was bad, or maybe we timeout over here. So the compiler actually put all of this code into a try block that has a catch exception on it, so it catches anything that goes wrong. So if anything goes wrong anywhere inside the state machine, it goes and takes the task, that's the task of int32 for HB length async, and instead of calling setResult on it, it calls setException. That causes this task to complete, but due to failure now, instead of due to the result. And again, this means that any other state machines that are waiting on this task, they will now wake up, and this exception will be rethrown to them so they can go and catch that exception and gracefully recover from it if that's what they would like to do. All right, there's one other thing that happens here that's a performance improvement. I'll mention it very briefly. The compiler inserts a little perf optimization line here that by the time this method returns, it's possible that the I/O operation is already complete. And so the compiler checks and says, well, if that operation is complete by the time this returns, then instead of queuing something up to the thread pool and leaving this method and coming back into the method, let's just go right to the next state of the state machine, and we'll just grab the result. And this just causes performance to improve a little bit because we're just continuing execution without having to leave this method and then have another thread pool thread come into the method to continue the state machine. So that's how that stuff works underneath the covers. Now, there are some limitations with what's available to you with async functions. You can't have your main method be async. However, in C# 7.1, which is not out yet, but they're working on it, they intend to remove this limitation. So your main method can be an async method, and you can do a wait inside main. But today that is not possible. You cannot mark a constructor as async. You cannot do property getters or setter methods as async. You can't do event add and remove methods as async. Async methods cannot have out or ref parameters. You can't do an await in an unsafe block. And you can look at the C# documentation to see all these limitations. For the most part, if you violate one of these, the compiler will issue an error and will not compile the code. And then you'll know that you're doing something that's just not allowed, and then you'll just go and fix your code. Okay. It is common, so now I'm just going to add some like icing to the cake, if you will, about this async await stuff. So it is common that within a single method, you might await multiple things. This is an example of a named pipe client that I had in a program that I worked on a few years back, where I newed up the named pipe client stream and noticed the pipe options asynchronous flag. This does the same thing as the file options asynchronous flag I showed you earlier, right? It tells the device driver to do those two things. Don't block a thread that's doing an IO operation on this named pipe, and put the completed ERP for the IO operation into the CLR thread pool. Then I connect to the pipe. Then I go and set a property on the pipe. What these things do is really not that interesting. Then I have a message that I want to write to the pipe. So I'm taking that message, which is a string, and I'm converting it to a byte array. Right? This is all compute-bound operations here. But then I want to call write async. This is an IO-bound operation. So write async, it does exactly what I told you before. It creates an IO request packet. It then internally calls read file, and then passes the IO request packet down to the kernel. Then the kernel goes and queues up the IO request packet for the named pipe device. And now, because we said file options asynchronous, our thread doesn't block there. Our thread returns from write async, which returns a task. In this case, I'm awaiting that task, and that allows the calling thread to return back to whoever called it. Again, if it's a GUI app, it can return back to the message pump and continue processing keyboard and mouse events. If it's a server-side app, then it's a thread pool thread that returns back to the pool so it can be used for doing other things. Sometime in the future, this write operation will complete. And when it does, the device driver will notify the thread pool. Then a thread pool thread will come out of the pool and will call this method, but it'll go to the next case of the state machine and execute the next line of code, where we will new up a byte array of 1,000 bytes. This is a compute-bound operation. And then we're going to call read async. Read async is going to create another IO request packet, send it down to the kernel, return a task, and then I await it. That allows the thread pool thread to return back to the pool. So now when the read operation is done, and the server, it could take an hour before it sends a reply back. So meanwhile, that thread was back in the pool doing other things. If an hour later, the server does send a response back, then the pipe driver will notify the thread pool. The thread pool will have one of its threads go and call this method again, but now it will continue at this await, where it will go and get the number of bytes that were read. Then it does some compute-bound work to process those bytes, and then here we have the close brace of the using, which will close the pipe, and then the close brace of the method, which will really signal this task to let anybody else who's waiting on that task to know this state machine has run to completion, and here is the string that we got back from the server as the result. And then that code can go and get that string and then do whatever processing it wants to do. Okay, how are we doing on time? 10 minutes to go before the Q&A part. If you look in the framework class library, you'll notice that there are many asynchronous functions that are there on all of the stream classes. So stream, which is a base class for file stream, network stream, crypto stream, memory stream, and so on. All of those classes have a read async, write async, flush async, copy to async methods. And all those methods do the same thing. They create an IO request packet, they send it down to the device driver, and then they return. And when the IO operation is complete, the thread pool thread will come in and resume the state machine if you await the tasks that are returned from these methods. There's a task reader class that has some classes derived from it, like XML text reader. And all those classes have read async, read line async, read to end async, read block async. Text writer has XML text writer, and it has various methods. The HTTP client, which is probably the most common of all these classes, well, that and the stream classes, has get async, post async, put async, delete async. They all send an ERP down to IO request packet down to the network device driver. Then it does the work and lets you know. And if you're talking to a database and you're using, let's say, SQL command, for example, then it has methods on it like execute database data reader async, execute non-query async, which again sends an IO request to the network driver. It goes and talks to SQL Server on the other side, and then when the SQL Server sends a reply back over the network driver queues up the response to the thread pool, and then the thread pool thread can notify you when it's done. And then there's other tools or utilities like Service Util. These tools produce web service proxy classes. These proxy classes also have async methods on them, which again do the exact same thing if you're making web service calls. The point I'm trying to make is that there's a lot of async methods in the framework class library, and all of these are there to allow you to use resources efficiently in the system while giving you this simple sequential programming model. Right? That's the purpose of their existence. All right, let me do these next two slides, and then I'll just stop for any questions. And these next two slides are, I think, really important because they really make it clear the benefit here. On the first slide, I'm showing you how to architect a non-scalable server. Now, why would you do this? Well, you wouldn't. But this is what most people do by default, and I want to show you why it doesn't scale. First, let me introduce the players. On the far left, I have, let's say, 3 users, and they're all using a browser. I picked the icon for Internet Explorer, but this could be Chrome or Firefox or anything. It doesn't really matter what this client is. I'm just picking like the canonical example where you have a browser talking to a web server. And this web server could be ASP.NET or it could be WCF or any technology. It doesn't matter what it is. But this is some server running on some machine somewhere, and it has a thread pool for doing processing of incoming requests, which I will walk you through in just a moment. And then when a client request comes into this server, it's very common for this server to want to make a request to another server, and it's very frequently that's some kind of database server like SQL Server or Mongo or whatever database that you like. It doesn't matter what it is. All right, so now let's walk through this. A client makes a network request that comes into this server. That's going to come into the thread pool initially, and the thread pool is going to have a thread that wakes up and starts doing some processing on behalf of that client. Now let's say that on behalf of that client, we need to make a request to the database server to go and look something up. We maybe need to get their address or their email or maybe authenticate them. Well, if we make this request synchronously, that is, we don't call an async method and we don't await it. We just do like what programmers have done for decades. Then the calling thread blocks in the device driver, and we're wasting the resource of this thread, waiting for this server to reply with a result. But we don't know how long that's going to take. This reply could come in an hour later. So let's say while we're waiting for this reply, another client makes a request to our server. Well, the thread pool creates another thread to go and process this second client request. And if that client request also makes a request to this server, then this thread blocks as well. So now we've created 2 threads with all their memory and all the time overhead of creating them, and now they're not running. They're sitting in the system idle. So CPU usage is near 0 on this machine because these threads are not running. They're I/O bound, they're not compute bound. And let's say a third client request comes in. Well, the thread pool creates another thread which also executes a request to the server, and then it blocks. And if we have lots of more client requests here, they all come in. The thread pool has to create more threads because there's no thread sitting in the pool ready to do work. So it creates more and more threads, but then those threads keep blocking because they're not in the pool. It doesn't know what they're doing. It doesn't know that they're blocked or not. And so it just creates more threads. You may recall earlier I told you this demo that I did not do for you, but I described it. If this is a 32-bit process, you can only create about 1,500 threads before you run out of memory. You get an out-of-memory exception and the process crashes. Well, if I get 1,500 client requests that come into here, we will run out of memory, an out-of-memory exception will be thrown, and the process will crash. And that is, of course, a horrible experience for those 1,500 and possibly more customers who are trying to hit your server. The point being, this doesn't scale, right? It's very inefficient use of resources, and you could only handle at most about 1,500 concurrent client requests. Any more than that, and the service crashes. To make matters worse, let's say that an hour later, this database server, it completes those 3 operations, and it sends all 3 results back. That causes those 3 threads to wake up, and now they're all running concurrently. But if we're running on a computer with only 1 or maybe 2 CPUs on it, we have 3 threads that want to run on a machine with only 1 or 2 CPUs. Well, the system can't run 3 threads on a 2 CPU machine. And so it has to pick 2 threads, run them, then context switch one away and put the other one on. So now context switching gets introduced, and now the performance of these threads is not as high as you would like them to be. So now we're not running at full speed. Eventually, all 3 of these requests will complete, and the threads can return back to the pool, and the HTML can be sent back to the clients. And now the threads can sit in the pool. And if the threads sit in the pool for a long time with nothing to do, then the operating system will kill them, and that will reclaim resources. That is good. We want that. If we have a lot of threads in the pool that are doing nothing, we do want to reclaim their resources. But as you can see, all in all, this architecture does not scale very well. Okay, so now let's walk through how to build a scalable server. I have the same players here, but we're going to do things slightly differently now. So the first browser makes a request into the server, a thread pool thread starts doing processing, and then it wants to go and make a request to the database engine down below. But here's what's different. When we make this request now, let's do it by calling an async method and await the result of it. This means that the thread's not blocked in the kernel waiting for the database server to reply. And instead, the thread can return back to the pool. This means that when the second client request comes in, the same thread can come out of the pool. Excuse me. And start doing some processing on behalf of the second client request. Now, it will also make an asynchronous request down to the server, and that allows that thread to return back to the pool again. And then for the third client request, the same thing happens again. Notice a big difference here. We've only need 1 thread, and we are processing all these client requests using just the 1 thread. And if I had 1,500 client requests, I could still use the 1 thread. And if I had 15,000 client requests, I can still use the 1 thread. And so my resource consumption is incredibly low, but my ability to scale is very high. All right, I'll complete this. So let's say an hour goes by, and the database engine at the bottom, it completes those 3 requests. Well, remember when you queue up things asynchronously, the completed ERPs get queued up to the thread pool, 1, 2, and 3. So now those are queued up in the thread pool. A thread pool thread can come out, process the first, and send the result. Then the same thread process the second, and then the same thread go and process the third. And now we don't have this context switching issue either, because I don't have more threads than I have number of CPUs. So I'm able to do all of this work, scale phenomenally well, very low resource consumption. And the secret to making all of that happen are these asynchronous IO operations. Okay, on that note, I will finish this and I'll take any questions that anybody might have for the next 15 minutes. I'm looking at the Q&A window. Does anybody want to post anything? Oh, let's see, I'm not scrolled up. I see there's a bunch of freezing. Okay, here's a question. Here, I'll move this down so you can see it. Wow, but that font is so tiny I can't see it. So I'm moving to my other monitor. What will happen if we create file stream without the special flag and then make read async? Great question. Then the device driver will not do the I/O operation asynchronously, and you will actually block. So you will not get any of the benefit. You must use that flag in order to get the benefit. It is mandatory. And then you say, what if we specify the flag, but then we make a synchronous call to read? Also a great question. Well, then the device driver will not block the thread, but read will block the thread, because basically it's going to get the task back, and then it's going to block waiting for the task to complete internally so it can return you the integer. So both of these are really bad choices. You're not getting any of the benefit at all, and you're using system resources very inefficiently. So you really have to use the flag, and you have to call the async method. Somebody can't hear. Audio. What OS do you use? I mostly use Windows 10, the latest version, on my Surface Pro 4 device. I also have a desktop at home that has 8 cores on it. And then if you want to know my mobile phone, I run Android on my mobile phone. I'm sorry for anybody who's had sound issues. I think it was recorded, yes. All right, here's a technical question. For example, some object, some field with read byte count equal await something with read async. If the return result of my await call will be handled in another thread from the thread pool instead of the original calling thread. So the answer to that is it depends. There's another aspect to this story that I didn't have time to go into, which is called the synchronization context. I do explain it in great detail in my CLR via C# book. The short version is that if a GUI thread goes and calls a method that doesn't await in it, then when the I/O operation completes, the thread pool tells the GUI thread to resume the state machine. So that means that your state machine will always be running on the GUI thread, is what that means. If it's not a GUI application, then yes, one thread can initiate the call and a completely different thread from the thread pool can be running after the await operation. So you can definitely have a thread switch there. And that's really ideal. That's what you want. You don't want to say, this is the only thread that can do this. You want to say, any thread can do this work. I don't really care which one. That allows you to scale better. Does that mean that I must take care of some locks to avoid problems for the main thread at the same time? No. Within a state machine, the compiler has generated a code in such a way to guarantee you that only one thread at a time will be in a state machine at a time. So if a new thread can't come into the await until the old thread has left the method. And the compiler has written the code in such a way to guarantee that for you. So that you don't have to worry about. So you don't have to take any locks because of that reason. Are there any pitfalls with asynchronous network sockets? I don't know. I had problems with timeouts in async sockets. Timeouts doesn't work when we do read async. Did you have any experience with this? That is true. And yes, I have some experience with that. Part of the problem, a big part of the problem is that when .NET was originally created, 15, 16 years ago, everything was synchronous. There really wasn't very much asynchronous stuff. People weren't doing it. And now that they're adding the async support, there are some rough edges that they haven't quite gotten to yet, like timeouts, as an example with sockets. The proper way to do cancellation, whether it's manual cancellation or timeout cancellation, is to use the .NET cancellation token. And almost all async methods take a cancellation token as their last argument. And you can pass that in order to cancel the operation. And you can create a cancellation token and say, when you new it up, I want this cancellation token to cancel itself in, let's say, 5 seconds. You specify how much time you want. And that's how you can do a timeout with that. So that's really the best way. Now, that being said, there are still some async methods in the .NET Framework class library today that do not take a cancellation token. I would say that those are bugs and that the team at Microsoft needs to go and fix those. There is a thing you can do to work around it. If you look online on the web, you can find some people like myself, and it's in my book, but other people too, have written a method called with cancellation. And that allows you to add cancellation support to an async method that doesn't take a cancellation token today. But hopefully Microsoft will just fix those in the future and give us that missing feature. So if the compiler turns our async method into a class, which represents a state machine, this means that if we heavily use async methods, we've got plenty of small objects created behind the scenes. So I wonder if there's any optimization made here. You have a very valid point. That is true. And it is one of the complaints that people have about this. There can be a lot of little objects that are created on the heap that will have to be garbage collected later. If you knew for a fact that I/O operations were always going to complete immediately, then everything I've talked about is a waste of time. And you would be worse off using it because of this additional overhead. The problem is that we don't know. I/O operations are unpredictable in time and duration, especially network ones, but even ones to hard disk. Some other program could be reading a file, somebody could be using Microsoft Word and opening a large document, and it's using the hard disk. So your program that's trying to just access a log file might have a hard time getting access to the disk because the Microsoft Word's trying to do something. So I/O operations are always unpredictable in duration. And so we're making a trade-off, and we're saying that by allocating these little tiny objects on the heap, we're avoiding wasting the large objects, which are the threads themselves. Now, if we could redesign, or if Microsoft could redesign .NET from scratch, I think they would do a lot of things differently to improve performance. They would make tasks be lighter weight. I'm sure they would make delegates and callbacks probably be value types instead of reference types. There's a lot of things that would be done, but it's hard to do those things now and maintain backward compatibility. So this is the system that we have. And for 99% of the people, this system works really, really well. And you can do some micro optimizations if you're really seeing that there's some problem. But you raise a good point. I'm pretty sure this is neglectable in the real world scenario, but if we're saying that thread context switch is expensive, then having all those objects might be expensive as well. Well, I think I just addressed that by answering the previous question. It's trade-offs. It's really all about trade-offs, and we don't know what the I/O operation performance is going to be. So we're taking some initial tiny perf hits in order to avoid a potentially long perf hit. And that's the trade-off. If we knew the I/O operations were always going to be short, we wouldn't be doing this. But we don't know. How many threads are defined, I guess, or are definitely, I'm not sure, are in the pool? So the pool has an algorithm on it where its goal is to have one thread per core. That's its goal. That's what it wants to have. But there are certain things that will cause the pool to go over that limit. If threads leave the pool and the kernel blocks those threads for some reason, so that would be a thread pool thread does a synchronous IO operation, or the thread waits on a kernel object like a semaphore or a mutex or an event, or the thread calls thread sleep, something like that, then the thread pool, the kernel actually notifies the thread pool and says, hey, thread pool, one of your threads has purposely put itself to sleep, so it's not using the CPU. And the thread pool will create additional threads because it wants to keep the CPUs busy. So maybe I'll say it this way. The goal of the thread pool is to keep all the CPUs busy. It wants to have no more than one thread per CPU to do that in order to avoid wasting resources and to reduce context switches. But if some threads of the pool are blocking, then the thread pool will go above that desired limit in order to keep the CPUs busy. If those threads wake up and return back to the pool, so the pool has a lot of threads in it that are doing nothing, then the thread pool will kill those threads off to reclaim the resources and shrink the pool back down. So the pool can dynamically grow and shrink depending on the load and what the threads as they come out of the pool, what they are doing. Do I have plans for a new book and for CLR via C#? I think about it all the time, quite honestly, and I am interested in doing it because of .NET Core, and I feel like .NET has a big life now on Mac and on Linux, but it's really hard for me to find the time to do that. So I would like to. I don't think it would take me a lot of effort, but it's still a challenge with my day-to-day job, and I got family and kids and everything else, so it's hard. And then I did just do that video series on architecting distributed cloud apps. That took a lot of time. In a way, I think of that as my new book, although it's a video series instead of a book. So I don't know, it might happen, but right now I'm not working on it, and I have no specific plan to do it or deadline. Could you add a couple words regarding configure await false? Well, what time is it? 11, 12? It's hard to explain that in a short amount of time, but I'll do my best because I know it's very confusing to a lot of people what its purpose is. So I mentioned earlier that this thing called the synchronization context, and I said that if you are calling await on a GUI thread, the synchronization context guarantees that the continuation of the state machine will also run on the GUI thread. This is really nice because it means that the code can update the list box or the combo box. It can manipulate the user interface because it knows it'll be running on the GUI thread. That's the good news. But sometimes you're writing code that let me phrase it this way. If you're writing a library, a DLL, that you could write a library that is application agnostic. That means that that library could be used by a console app or a GUI app or ASP.NET, right? It doesn't matter. And actually, most of the framework class library is that way, right? I could use the file stream class from a console app. I can use file stream from ASP.NET. I can use file stream from a GUI app, right? It works in all of those. So file stream, like almost all the classes in the .NET framework, like except for the XAML classes, right? They are application model agnostic. So here's the short version. If you are building a library that is not tied to an application model, right, can be used in any kind of application, then you should be using configure await false on every await you have in your code. What that does is it tells the compiler not to capture the calling thread synchronization context. And that means that any thread can resume the state machine. It doesn't have to be the GUI thread. And that just makes things faster. Capturing the synchronization context is a perf hit. And if it's a GUI synchronization context, then the thread pool has to notify the GUI thread to do the work. So there's additional perf hit that happens there. So, and then there's some deadlock scenarios that you can get into, which you will avoid if you call configure await false. Again, in my CLR via C# book, I go into this in excruciating detail. So, but the short version is, if you're writing an application model agnostic library, you should be using configure await false everywhere. Where are all the queued async requests placed before return to the thread pool? Well, they're placed in the ERP, I guess, is the answer to that question. Like the callback method of who to call, that's actually put in the IO request packet that's sent down to the driver, and then the driver queues the completed ERP to the thread pool, and embedded in there is the address of the callback method to be invoked when the operation completes. So I think that answers that question. I know we're really close on time. I can maybe do one or two more and then we'll stop. Is it better to create a new thread than use the thread pool thread if you're going to do some big, how big should it be, CPU-bound work? It's hard to say. It's hard to say. I would encourage you to try to use the thread pool even for long-running CPU-bound work. And if you are running your application and testing it and profiling it, and you're happy with the results, and I think most of the time you will be happy with the results, then I would leave it exactly like that. If for some reason you're not happy with the results, then you could go and create a dedicated thread. I'll add another thing to this. If you are going to be executing a very long-running CPU-bound operation, which by the way is very rare, maybe you're doing some kind of long-running statistical analysis, but usually it's very rare that you're doing a long-running compute-bound thing. If you are doing that, another thing that you might consider is lowering the priority of that thread. So that way, if other threads are trying to do, more useful work, they will preempt your low priority thread and get more CPU time. If you have a long-running compute-bound thing, it's using a CPU, then you're maybe stealing that CPU. Yes, context switching will happen, but you're slowing down all the other threads because you've introduced the context switching. If you lower your thread's priority, then anything that's higher priority will run and preempt you, and your long-running thing will just get whatever spare CPU cycles are left over. All right, it's 11:17. I don't think I can get to the rest of these. Well, there's two. All right, I'll try really quick. What would be the best async solution for a server which is calling through the network but never being called? And there is a complicated logic depends on which response it gets. Best async solution for a server which is calling through the network but never be. So I don't know if that means you execute operations based on time or you're basically just running in an infinite loop. I don't quite have enough information to know the best way to do that. If it is time-based, though, you would usually just tell the thread pool to call some method at some timed interval. So you're not receiving client requests. Instead, you're using the timer as affecting a client request in effect of. And then, yeah, making your outgoing request should always be done asynchronously, no matter what. But the asynchronous flag is not available for hardware, is it? For example, if I need to work with the HID device, so it must be supported by network in order to do that right. Yeah, that's either true, or you might have to p-invoke out from .NET and call the native Windows functions directly. For a lot of hardware devices, you can call the Win32 function device IO control, and it allows everything to be done asynchronously in device IO control. So there may not be a .NET wrapper at all for some devices, or the wrapper may only offer synchronous, not asynchronous support, and that just means the guy who wrote the wrapper didn't do a good job. But you can p-invoke out to Win32 and fix it yourself, or you live with it if you can live with the extra overhead. All right, ladies and gentlemen, we'll call it here. That was the last question I got. So I hope you enjoyed the session. Thank you very much. And I guess that's it. We'll say goodbye. Bye-bye.
Thank you everyone for joining us. So now you'll have a chance to fill in a short survey just to make our webinars better. And if you're interested to see the recording of this webinar, you also can join us on social media and you'll be able to see it in a few days' time. And thank you very much, Jeffrey, for this speech. It was great to hear you, and I hope we'll see you back sometime soon.